Hello again. In this part of the talk, I will describe a few more applications of our methods, which are under the umbrella of scalar and mean curvature comparison. So the first thing is a normal radius estimate. So what is this about? So before going through the statement of the theorem, what we want to do here is we have some manifold with boundary. And we look at the largest radius such that the normal exponential map of the boundary is still a diffeomorphism. And that is what is called the normal radius here. Just to note it like this. And the idea is that under certain assumptions on the scalar curvature and the mean curvature of the boundary, we can actually say that this normal radius is not too long. This is sort of similar to this bandwidth estimate, but sort of slightly different setup. And the theorem that we have here is to the following situation, that here we have a compact spin manifold again, which is even dimensional here, and it has a boundary, and there is an assumption on the double. And the double is the manifold that you obtain by sort of gluing the manifold to itself along the boundary, and you put the sort of opposite orientation on the other half, and then it sort of fits together to an oriented spin manifold again. And there is a condition on this double here, namely that it should have infinite A-hat area. This is a notion that you're probably not familiar with, and I also don't want to define it in detail. The point of this is that this is yet another condition that implies that the double does not admit the metric of positive scalar curvature. So this is an obstruction to positive scalar curvature. And sort of examples of manifolds with infinite A-hat area. That includes, for instance, enlargeable manifolds like the torus, e.g. torus. So for instance, here you could just, an example of this would be to take half of the torus, such that if you double it, that you get the full torus, and then you could apply the theorem to it. And sort of more generally, manifolds of infinite K area. This is sort of a notion due to Gromov. Yeah, the infinite A-hat area is like for spin manifolds, a slightly more general condition than A-hat than K area. But I don't want to define it here in detail. What's important is that this is a condition that implies that the double does not admit a metric of positive scalar curvature. And in fact, if you assume this now and you put conditions on scalar and mean curvature, namely that the scalar curvature is bounded below by our favorite normalization constant n times n minus 1. And again, the mean curvature of the boundary here is bounded below by a negative number, which again is the tangent of some argument where the argument is nl/2 and L is strictly in between 0 or pi over n. Then again, one can conclude that this normal radius is bounded above by L. And in particular, like in the bandwidth estimate, one can conclude from this, because this here goes to minus infinity as L approaches pi over n, that the normal radius always must be strictly smaller than pi over n, under this assumption that the scalar curvature is bounded above by n times n minus 1. All right. And maybe to connect this with a few other results. In particular, of course, this means that the mean curvature cannot be non-negative. So you cannot have a mean convex boundary and a positive scalar curvature under these assumptions. This is can be seen differently, because if you have a mean convex boundary and positive scalar curvature, then you can actually double the metric and smooth the metric near the interface in such a way that you get a metric of positive scalar curvature on the whole double. And as I said, this condition here is precisely a condition that obstructs positive scalar curvature on the double. So you cannot have that. And this is sort of, in a sense, already has been known for a long time. So this idea of doubling and smoothing goes back to Groff and Lawson, has been also worked out by Almeida in the 80s. And in a more recent paper by Beer and Hanke from last year, there's sort of a family version of this. So this is kind of, can be seen differently, but this is sort of a quantitative refinement of the fact that you cannot have positive scalar curvature with mean convex boundary. You can actually sort of make this more precise and say something about the distance. And here, again, this estimate here, or even this estimate here, can be seen to be optimal. And you can actually see it using the same kind of example as in the bandwidth estimate case. So you again now look at this manifold here, torus cross an interval. This is precisely what I mentioned. Take kind of half of the torus of one dimension above, and you put this product metric that we had. And one then sees that if you now consider not two different boundary components which play a different role, but take the whole boundary here with the two components and consider it as one boundary, then this fits into the theorem, and it shows you that this estimate here and this estimate here is actually optimal and cannot be improved. All right, this is sort of the first other application, which if you now look at this example, is actually very similar to the bandwidth estimate. All right, then the next thing I want to mention is Gromov's long neck problem. So before I mention this problem, I want to remind you of an older theorem, which has, however, recently gained importance again, and this is in the center of a lot of recent work of Gromov on metric inequalities and so forth. And this is Yahoos Theorem, which tells you that the standard sphere has a certain extremality property with respect to scalar curvature. More precisely, the theorem tells us if you have a closed spin manifold of some dimension n bigger than 2, bigger or equal than 2, and it has scalar curvature bounded below by n times n minus 1, which is our favorite normalization constant, which is the scalar curvature of the standard sphere. And if you then take any smooth area non-increasing map from M to the n sphere, such that it has a non-zero mapping degree in the topological sense, then it actually must be an isometry. Yeah, and in particular, you could take F to be the identity here and consider sort of different metrics on the sphere. And then if you take another metric, then the standard metric, which, however, has sort of infinitesimally bigger areas than the standard metric, then this theorem tells you actually this cannot happen. And the only way to have this is that this metric is already the standard metric. All right, maybe I should sort of say to fix it precisely, area non-decreasing here means that this means sort of in the infinitesimal sense that sort of the induced map on two vectors that this one is not, it does not increase the norm with respect to sort of the induced norm on two vectors by the Riemannian metric. All right, now this is sort of a theorem about closed manifolds. And now sort of Gromov, the last years asked the question, if there is a slightly modified version of this for manifolds with boundary, where you get an estimate, which is very similar to this bandwidth estimate. And sort of the, I will now state you a theorem that sort of captures this question. So the statement that we have here is that if we have n-dimensional Riemannian spin manifold with boundary, and again we have our scalar curvature assumption, and for technical reasons here we have to assume that n is even, and again we take an area, a non-increasing map from M to the sphere, and now we want to sort of impose a similar condition as above, non-zero mapping degree, but there we have to be a little bit careful, because sort of in general, it doesn't really make sense to talk about the mapping degree of a map from a manifold with boundary to a closed manifold. So to do this, one needs to impose an assumption, and one possibility for this to make sense is to require that the map is actually constant near the boundary. Yeah, and this is actually what we're gonna assume here implicitly in the following sense. And we will assume that again for like before, for a number L smaller than pi over n, we now assume that the distance between the boundary of the manifold and the support of the differential of the map that we consider is bounded below by L. That means that in the L neighborhood around the boundary, the map is constant. Now that's what it means, because that means that the differential is zero in this L neighborhood. That's precisely what's written here, and therefore the map is going to be locally constant near the boundary, in case the boundary has multiple components, and we allow that. All right, so that's sort of the first condition. And the second condition is, again, a mean curvature condition, and which is analogous to what we had before. And under this assumption, the statement now is that in this case, the mapping degree is zero. Now, this is kind of a version for manifolds with boundary of this in a certain sense, but stated in the contrapositive way. And in particular, what this means is that if the distance that we have here is too large, so it's larger than pi over n, then the mapping degree must be zero, independently of any assumption of the mean curvature. And again, this is follows because this expression here goes to minus infinity as L approaches the critical threshold of pi over n. And in fact, sort of this implication here is the question that Gromov asked whether it holds. And this is sort of Gromov's long neck conjecture. And this was originally, like without the mean curvature refinement, proved by Simone previously in a previous paper. All right, and maybe sort of to visualize a little bit what's happening here, let me also mention that this estimate that one gets here is actually optimal again. And here, again, what one can do is one can sort of take our favorite product example. And sort of I'm going to draw this like schematically like this. And so let's say this could be something like Ti minus 1 cross some constant, some interval. And now the idea is you want to have a map to the sphere, and you want to have it in such a way that the areas don't get increased, and ideally you want to also achieve that the map isn't sort of that there is a support of the map which is there, and you want to get this sort of reasonably large so that you can kind of at least approximately show that this is optimal. And for that reason, one can do the following. The idea is now one does a Watt product like before to make the scalar curvature equal to n times n minus 1. So this is sort of possible with using a Watt product metric. Like this. But now, in order to make the sort of area, you want to produce a map of non-zero degree to the sphere, and you can actually do it. So you can think about how to do this, but you can sort of take a sort of small strip around this n-1 torus here, and then think about that this is actually possible to map to the sphere of non-zero degree, and in such a way that it is a constant outside this small strip. So it kind of fits together with a sort of constant map on the outside. So sort of this F should be in such a way that this red part here is the support. And sort of this all possible. So, and sort of the only issue that might now arise is that it's not so clear how to rearrange this area non-increasing part, because you have just chosen a map, and then you have defined this in a very small part. So you kind of imagine that if you map that to the standard sphere, that you need to sort of increase some direction, and then you might decrease. You might also increase areas this way. But now, sort of the crucial trick is to make sure that this sort of vertical direction here, sort of the torus direction here, that this is large. And now, if you make that sort of large, you can make it as large as you want. You can kind of, when you write down this map to the sphere, you can sort of contract this direction, and then that allows you to compensate for any sort of increase that you need if you enlarge this small strip here. So in a certain sense, you can arrange in such a way that the area of the strip here is still sort of comparable to the area of the standard sphere, even though you make this very small. And by making it very small, you can kind of get this distance here to be approximately L. Yeah, sort of the distance between the support and the boundary, you can sort of approximate L, and sort of this kind of construction. Now, if you make it precise, and that's possible, I can show you that this here is actually optimal. Yeah, and sort of here we see that we actually, for this construction, we kind of need to make use of the area non-increasing part if we instead assumed that we want our map to be length non-increasing, then sort of this kind of example wouldn't work anymore. All right, this was the long neck problem. And finally, I want to explain a kind of another kind of version of Yahoos theorem for manifolds with boundary, which is a theorem about annuli in space forms of arbitrary constant curvature. So here we take an n-dimensional simply connected space form of some constant curvature, so either the sphere, hyperbolic space, or Euclidean space, and then you consider an annulus around some base point in your space, and so you kind of choose two radii, t minus and t plus, and you assume here, in addition, that in case you do deal with the sphere, so in the positive curvature case, you assume that this the sort of you don't go all the way to the opposite point of the base point. Yeah, so in the case where you have the Euclidean space or hyperbolic space, you can take an arbitrarily large compact annulus, but in the spherical case, you don't go all the way. You just really consider the proper annulus, which doesn't close up on the other side. That's why you put this upper bound here. And now, if we assume that we have such an annulus, and now again, for technical reasons, we focus here on a certain parity of the dimension, namely on odd dimensions now, and we take a Riemannian metric, another one, not necessarily the standard one, on this annulus, but under the assumption that the metric here is bounded below by the standard metric. That means this means sort of with respect to length of vectors. That means if you sort of compute the length of tangent vector with respect to G, this should be larger than the length of the same vector with respect to the standard metric G kappa of constant curvature kappa. And also we assume that the scalar curvature of the metric is bounded below by the scalar curvature of the standard metric, that is kappa times n minus 1. And again, the mean curvature of the boundary should be bounded below by the corresponding mean curvature of the standard metric. And this is sort of it's just an explicit number. Again, it's the cotangent function corresponding to this curvature. So the picture is this. You have your annulus, and sort of you have these two boundary components, the outer and the inner boundary. And it's sort of always my convention that the mean curvature is computed with respect to the interior normal field. And then you assume this lower bound here. This means that it holds here and here on both boundary components. So this holds on. And then the conclusion of the theorem is that this metric must already be the standard metric. So you cannot simultaneously increase the scalar curvature, the mean curvature, and length of the vectors starting from the standard metric in an annulus in a space of constant curvature. This is just not possible. The only way, if you have this bounds, is that you already are the standard metric. So this is kind of yet another rigidity result for metrics in which is kind of comparable to like Yahoos theorem, but sort of here the sort of crucial difference is that we focus on lengths here, and also we actually allow arbitrary curvature here. So sort of the reference space is any annulus, and it in particular also allows the case of negative curvature. And here you might be a little bit confused if you think about it a little bit, that how is it possible that you have a kind of extremality result for negative scalar curvature? Because if you think about having a space of negative scalar curvature, then you can just rescale the metric a little bit, making it bigger, and that's in sort of absolute value terms decreases the curvature, and therefore it sort of, if the curvature is negative, it actually increases it, right? And so if you just have a closed manifold of, let's say, negative curvature, then you can never have an extremality result of this kind. But here the crucial point comes in is that we actually need these boundary components. So the mean curvature, let's say in the case of an annulus in hyperbolic space, here the mean curvature of the outer boundary would be negative, and therefore if you do a simple rescaling trick, you cannot violate this theorem. So here this kind of part in the negative curvature situation really crucially needs the boundary, and it wouldn't work if you didn't have a boundary. All right, and maybe I should also mention that we actually here I have stated sort of a simplified version of the actual theorem that we have. Sort of we have a more general Watt product comparison theorem, which works in sort of more general Watt products under certain assumptions, and sort of the case of an annulus in a space form is just sort of a particular case of a nice metric that you can write down as a Watt product. And sort of this is the last part of my part where I want to explain results, and I will make another pause here, and in the next and final part of this talk I will explain the methods of proof that go into all the theorems, because in a sense they are all based on the same technique.